The forest floor appears at first glance to be a quiet layer of fallen leaves and filtered sunlight. But as the camera lowers and steadies, a different architecture emerges, one built not of stone or steel, but of soil, saliva, and living bodies. Narrow trails, polished by constant traffic, radiate outward in deliberate lines that cut through the undergrowth with the precision of engineered roads. Along these pathways, fragments of fresh green leaves move in steady procession, carried above the heads of workers like pieces of cargo on a living conveyor belt. Each fragment trembles slightly as its bearer adjusts to shifting terrain, but the line never breaks. Beneath this network lies the true structure, a subterranean city whose complexity rivals that of any human fortress, constructed by the collective labor of millions of leafcutter ants. The entrance to the colony is not a single opening, but a guarded threshold system, often marked by small mounds of excavated soil arranged in subtle domes. These mounds serve both as ventilation chimneys and as drainage architecture, preventing flooding during heavy rains. Air is drawn through the nest by temperature gradients between shaded forest floor and deeper, warmer chambers, a passive thermoregulatory system that stabilizes humidity and carbon dioxide levels. Within, the colony descends into layered chambers carved into compacted earth, some as large as a small room, others narrow corridors connecting sectors with deliberate efficiency. At the center of this underground fortress lies the true objective of all this effort, a living fungus garden. Leafcutter ants do not eat the leaves they harvest. Instead, they cultivate a specific fungal symbiont, carefully feeding it with freshly chewed plant pulp. The leaves are processed in stages. Larger workers slice foliage from trees, selecting species with chemical profiles suitable for cultivation, while smaller workers ride atop the leaf fragments during transport, defending them from parasitic flies that attempt to deposit eggs in transit. Once inside the nest, the leaves are further cut, cleaned, and inoculated with fungal mycelium. The ants prune away contaminating molds with surgical precision, and specialized worker castes remove waste to distant refuse chambers to prevent infection. The fungus, in turn, produces nutrient-rich swollen hyphal tips that serve as the primary food source for the colony. This is agriculture practiced at scale, a system refined over tens of millions of years through coevolution between ant and fungus. Humidity within the fungal chambers is maintained within narrow tolerances, typically above 80%, because the cultivated fungus is sensitive to desiccation. Workers constantly adjust chamber walls, sealing cracks with soil pellets, and opening microvents to balance moisture. If carbon dioxide accumulates beyond safe thresholds, airflow routes are modified through new tunnels. The colony's survival depends on maintaining these environmental parameters with remarkable consistency. The ants possess no central planner, yet through local behavioral rules, responding to temperature, moisture, and chemical cues, they collectively regulate their subterranean climate with astonishing accuracy. This emergent regulation functions much like a decentralized control system, where thousands of small corrections produce stability across an entire city. The defensive design of the colony is as deliberate as its agricultural infrastructure. The trails that extend from the nest are not random foraging paths. They are arterial routes connecting to reliable plant sources, sometimes stretching hundreds of meters through dense forest. Along these routes, patrol workers move in both directions, sampling chemical signatures in the air and on the ground. If an intruder approaches, a predatory beetle, a rival ant species, or even a curious vertebrate, the response is not chaotic retreat. Instead, the nearest workers release alarm pheromones that ripple through the column like a silent siren. Within seconds, the traffic pattern changes. Leaf carriers drop their burdens and pivot, mandibles opening, bodies raised. At the nest entrance, larger soldier ants position themselves as barricades. Their heads, disproportionately large and armored, can plug tunnel openings entirely, functioning as living doors. If the threat persists, waves of medium-sized workers surge outward along the trails in coordinated counterattack. They do not disperse randomly. They advance along established routes, maintaining contact through pheromone trails that ensure reinforcement arrives precisely where needed. Mandibles clamp down with crushing force relative to their size, and some species supplement mechanical force with chemical sprays derived from venom glands. The effect is not a scattered skirmish, but a layered defense strategy. Perimeter detection, entrance blockade, then outward expansion to overwhelm and repel. Predator-prey interactions along these trails are constant and often subtle. Parasitic phorid flies hover above the columns, timing their egg-laying attempts to moments of distraction. A fly darts in, deposits an egg on a worker's thorax, and escapes before a defensive bite can land. If the larva succeeds in developing, it may eventually decapitate its host from within, a macabre but biologically efficient life cycle. Yet even this pressure shapes colony behavior. Workers adjust their activity patterns during peak fly presence, increasing the number of small hitchhiker ants that ride leaf fragments and actively swat at approaching parasites. The ecosystem surrounding the trail is not merely background scenery. It is a dynamic battlefield of evolutionary countermeasures. Thermoregulation extends beyond the nest interior. Foraging schedules often align with temperature windows that maximize efficiency, while minimizing desiccation risk. During intense midday heat, traffic may slow or shift to shaded routes. The ants' exoskeletons, though protective, limit water retention, so activity patterns are tuned to microclimatic gradients within the forest. Even the placement of trails can reflect subtle differences in canopy cover, humidity pockets, and plant chemistry. Over time, the colony sculpts its landscape into a semi-permanent network, pruning vegetation and compacting soil in ways that alter nutrient cycling and seed dispersal. Leafcutter ants are not simply inhabitants of the forest floor. They are ecological engineers whose agricultural demands reshape plant communities and influence carbon flow. Inside the nest, caste specialization reinforces efficiency. Smaller workers tend the fungal gardens with delicate precision, constantly grooming surfaces to remove competing microbes. Larger workers excavate new chambers, transporting soil upward, grain by grain. Soldiers remain stationed near vulnerable junctions. The queen, deep within the most protected chamber, serves as the reproductive engine, laying thousands of eggs each day. Yet even she depends entirely on the workforce to maintain conditions suitable for her survival. The fortress is not designed for individual glory, but for collective persistence. When the colony faces large-scale disturbance, such as flooding from torrential rain or attack from a mammalian predator, the defensive response escalates beyond localized counterattack. Workers swarm en masse, covering exposed surfaces and biting repeatedly, their numbers alone forming a deterrent. If a breach threatens the fungal chambers, emergency repair begins immediately, soil packed rapidly into compromised walls. The priority is always the garden. Without the fungus, the colony collapses. Every defensive surge, every trail reinforcement, ultimately protects that living crop beneath the earth. From above, the procession of leaf fragments continues, steady and unbroken, each piece destined to be transformed into sustenance through a partnership older than many forest trees. The city fortress persists not through brute strength alone, but through coordination, agriculture, environmental engineering, and layered defense strategies that respond dynamically to threat. Beneath the quiet hum of the forest, an empire of soil and fungus thrives, expanding outward in calculated lines, ready not merely to withstand intrusion, but to surge outward in unified counterattack whenever its living foundations are challenged. Morning light settles over a meadow thick with flowering clover and wild thyme, and at its center stands what appears to be an ordinary wooden hive box, unassuming against the vastness of field and sky. Yet within its walls exists a fortress constructed not of timber, but of wax engineered by living bodies and maintained by thousands of coordinated minds. The hum that emanates from within is not random noise. It is the collective respiration of a superorganism, a colony of honeybees whose survival depends on architecture, thermodynamics, chemical communication, and a security system as disciplined as any fortified stronghold. The entrance, no wider than a narrow slit, functions as a single checkpoint through which every departure and return must pass. Above and beyond this opening rises a world of comb, precise hexagonal chambers built from wax secreted in delicate scales from the abdomens of worker bees, molded and measured by antennae and mandibles with geometric accuracy that minimizes material while maximizing strength. Inside, the air is warm and stable despite fluctuations outside. Honeybee colonies maintain brood nest temperatures within a remarkably narrow band, typically around 35 degrees Celsius, even when external conditions swing dramatically. This thermal constancy is not incidental. Developing larvae are highly sensitive to temperature shifts, and even minor deviations can affect wing formation or neural development. To achieve this regulation, worker bees generate heat by contracting their flight muscles without moving their wings, a behavior known as shivering thermogenesis. Clusters of workers form living insulation around brood cells during cold spells, trapping heat within the comb. In excessive warmth, other workers line the entrance and interior corridors, beating their wings in coordinated ventilation patterns that draw cooler air inward and expel carbon dioxide and excess moisture. Water foragers return with droplets collected from nearby sources, spreading them thinly across cell rims so evaporation can carry heat away. The hive breathes, cools, and warms through distributed labor, each bee responding to local cues of temperature and humidity without centralized command. The comb itself reveals layers of purpose beyond simple storage. Upper chambers brim with capped honey, thickened by evaporation to prevent fermentation and sealed beneath wax lids for long-term preservation. Adjacent cells hold pollen packed and fermented into bee bread, a protein-rich resource critical for larval growth. Deeper in the core of the structure lies the brood nest, where the queen moves deliberately from cell to cell, guided by pheromonal gradients and the attentive grooming of her retinue. She deposits eggs in a pattern that maintains optimal spacing, ensuring that heat generated by workers distributes evenly. The hexagonal architecture, long admired for mathematical efficiency, also provides mechanical resilience. Interlocking walls distribute stress across the comb, allowing it to bear the weight of honey stores that can reach many kilograms without collapsing under gravity. What appears fragile from the outside is in fact an adaptive lattice tuned by evolution to balance economy and durability. At the hive entrance, guard bees assume their positions. They are not a separate caste, but workers of a certain age whose physiological state aligns with defensive roles. Each incoming bee is met with close inspection. Antennae tap and sweep across the body surface, sampling cuticular hydrocarbons that encode colony identity. These chemical signatures are shaped by shared diet and environment, and they function as passports. A returning forager carrying nectar or pollen is allowed through with minimal delay, while a drifting bee from a neighboring colony may be seized, grappled, and forced away. The checkpoint is dynamic. During periods of nectar abundance, tolerance may increase slightly to accommodate heavy traffic, but when resources are scarce or robbing attempts intensify, scrutiny becomes severe. Predatory threats hover beyond the entrance. Wasps patrol in late summer, testing the vigilance of guards, attempting to dart inside and seize a worker or steal honey. If a wasp breaches the threshold, the response is immediate and collective. Nearby bees release alarm pheromones from their mandibular glands, notably isopentyl acetate, which carries a sharp scent detectable even to human observers. This chemical signal adheres to the intruder's body, marking it as a focal point for attack. Workers converge, biting and stinging in rapid succession. The barbed sting of a honeybee lodges in the elastic skin of mammalian predators, anchoring as venom sacs continue to pump toxins even after the bee tears free, an act that costs her life, but amplifies the defensive signal. In encounters with other insects, where barbs do not anchor, bees may sting repeatedly. The venom contains compounds that disrupt cell membranes and amplify pain, but its function extends beyond immediate injury. It acts as a rallying beacon, intensifying aggression in nearby defenders. The escalation from inspection to counterattack unfolds within seconds. A single sting releases alarm pheromone that spreads across the entrance, and the colony shifts from routine foraging to defense posture. Guards raise their abdomens, wings vibrating in short bursts, broadcasting both chemical and acoustic cues. Workers deeper within the hive detect the signal and surge forward in a coordinated wave. The visual effect is striking. Bees spill outward in a thickening cloud, orienting toward the threat source with precision guided by scent gradients. They do not pursue randomly, but concentrate on the marked target, maintaining cohesion as they drive it away from the entrance. This collective aggression is costly, as stinging can mean death for the defender. Yet natural selection has favored such self-sacrifice because the survival of the colony outweighs individual longevity. The hive operates as a single reproductive entity, with the queen as its genetic nucleus and workers as functional extensions. Defense extends beyond stinging. In regions where larger predators such as hornets threaten colonies, honeybees may employ thermal defense. Workers swarm around the intruder, forming a dense ball that traps it within their bodies. By vibrating their flight muscles, they raise the temperature inside the cluster above the tolerance threshold of the hornet, while remaining just within their own survival limit. Carbon dioxide levels also increase within the ball, compounding stress on the invader. The hornet succumbs to heat and suffocation, while the bees disperse and resume their posts. This tactic reveals a sophisticated exploitation of physiological differences between species, turning the colony's thermogenic capacity into a weapon. Beyond immediate threats, the hive's fortress logic includes redundancy and resilience. Should disease infiltrate the brood, hygienic workers detect infected larvae through subtle changes in odor and remove them before pathogens spread. This behavior, shaped by selective breeding in some managed populations, reduces vulnerability to parasites such as varroa mites. Communication about distant food sources occurs through the waggle dance performed on vertical comb surfaces, where returning foragers encode direction relative to the sun and distance through duration of vibration. This navigational system integrates celestial cues, polarized light perception, and internal circadian rhythms, allowing bees to adjust their orientation as the sun arcs across the sky. Even this foraging communication influences defense, because resource abundance strengthens colony vigor, while scarcity can heighten defensive intensity as stores become more precious. As the day advances and sunlight warms the meadow, the entrance remains active but controlled. Foragers depart in steady intervals, while guards continue their inspections with unwavering focus. The wax walls glisten faintly in filtered light, their surfaces alive with subtle movement as workers pass messages through touch and scent. The fortress holds not through isolation, but through perpetual vigilance and cooperation. When alarm ripples outward and defenders launch in a coordinated wave, the response is neither chaotic nor reckless. It is an evolved algorithm executed by thousands of individuals acting as one. In this living citadel of wax and wings, architecture, chemistry, and collective behavior merge into a defense system refined across millions of years, ensuring that the hum within continues, steady and resilient against the shifting pressures of the surrounding world. A weathered wooden beam beneath the eaves of an old barn appears solid and unremarkable, sun-bleached on the surface, grain lines etched by seasons of wind and rain. Yet a closer view reveals a perfect circle bored into its side, no wider than a fingertip, its edges clean and deliberate. From this aperture, a dark shape emerges briefly, iridescent wings catching the light before vanishing back into shadow. The carpenter bee does not construct with wax or soil. She engineers with absence, removing wood fiber grain by grain to create a fortress concealed within the structure of trees, fences, and timbers. What seems like damage to human eyes is, in ecological terms, an architectural solution refined by evolutionary pressure. A narrow entrance leading to a corridor that turns sharply and branches into brood chambers hidden deep within solid wood. The female carpenter bee begins her excavation in spring, selecting untreated, relatively soft wood where her mandibles can grip and shave fibers efficiently. Her jaws are not only cutting tools, but sensory instruments, testing density and moisture as she works. She chews a circular tunnel straight inward for several centimeters before angling the corridor along the grain, creating a passage that may extend the length of a forearm or more. The geometry is intentional. A single narrow entrance reduces exposure to predators and parasites, and the right-angled turn prevents a straight line of sight into the brood chambers. Inside, she partitions the tunnel into a series of cells, each provisioned with a mixture of pollen and nectar shaped into a compact mass. Upon this nutrient reserve, she lays a single egg, then seals the chamber with a plug of chewed wood pulp. The sequence repeats, forming a linear nursery in which the oldest larvae develop closest to the exit, ensuring that emerging adults do not disturb younger siblings deeper within. The architecture itself becomes the primary layer of defense. Unlike social bees that rely on large colonies for protection, carpenter bees are largely solitary, and their survival depends on design efficiency rather than numerical advantage. The entrance hole functions as a choke point. Any predator attempting to reach the brood must compress its body and enter head first. This constraint favors the defender. The female positions herself just inside the opening, her abdomen facing outward, capable of delivering a sting to intruders that force their way through. Her large body effectively plugs the corridor, transforming herself into a living barricade. Even when not actively blocking, the narrowness of the tunnel prevents larger predators, such as birds or small mammals, from accessing the chambers. Architecture substitutes for walls and soldiers, converting a simple wooden cavity into a defensible stronghold. Predation pressure shapes every aspect of this design. Woodpeckers, for instance, are known to detect the faint vibrations of larvae within timber and may chisel through wood to extract them. In response, carpenter bees often select beams beneath protective overhangs or areas where vibration signals are dampened by surrounding material. Parasitoid wasps, equipped with long ovipositors capable of drilling into wood, represent another threat. Some wasps can sense the location of bee larvae through chemical cues or subtle acoustic feedback, inserting eggs directly into sealed brood cells. The bee solution lies partly in tunnel depth and partly in timing. By staggering egg-laying and sealing each chamber individually, she reduces the window during which a larva is vulnerable before pupation. The sealed partitions also limit the spread of fungal contamination, creating microenvironments that buffer humidity and microbial intrusion. Within the tunnel, temperature and moisture fluctuate less dramatically than outside. Wood acts as an insulator, slowing heat exchange and retaining moderate humidity. This stability benefits developing larvae, which rely on consistent conditions for proper metamorphosis. The bee does not actively ventilate her nest as social species do, yet the tunnel's orientation along the grain and its limited opening regulate airflow passively. Warm air rises and escapes slowly, drawing in cooler air from the entrance without creating drafts strong enough to desiccate provisions. The simplicity of the system belies its effectiveness. By embedding her brood within a thick wooden matrix, the carpenter bee leverages the physical properties of her environment as a form of environmental control. The adult female's behavior reinforces this defensive architecture. She exhibits site fidelity, often returning to the same tunnel year after year, expanding it or creating adjacent galleries that branch from the original shaft. Over time, a single beam may contain a network of interconnected corridors, each one a generational layer of occupation. Although carpenter bees are not eusocial in the strict sense, some species display a form of cooperative nesting in which daughters remain in the natal tunnel, assisting with defense or maintenance. This limited sociality adds another dimension to protection, as multiple adults can guard separate entrances or share vigilance duties. The presence of even one additional defender significantly increases the deterrent effect at the choke point. Outside the entrance, males patrol territories with conspicuous hovering displays. Lacking stingers, they rely on bluff rather than force, darting aggressively toward perceived threats, including humans, in rapid, erratic flights. Their large eyes are adapted for detecting movement, allowing them to intercept rivals or potential predators before they approach the nesting site. This aerial vigilance complements the static defense within the tunnel. While the female secures the corridor, the male's patrol creates a buffer zone, a behavioral perimeter that discourages intrusion. The combination of structural and behavioral defenses forms a layered system in which architecture narrows access and active guardianship deters approach. The ecological role of carpenter bees extends beyond their hidden fortresses. As powerful pollinators, they perform buzz pollination, vibrating their flight muscles to release pollen from flowers that require mechanical agitation. This behavior, essential for certain plant species, underscores a duality. The same musculature used for territorial display and thermogenesis also enables effective pollination. In cooler mornings, females may bask at the tunnel entrance, absorbing sunlight to elevate body temperature before flight. Thermoregulation in solitary bees relies on both behavioral positioning and muscular heat production, and the wooden nest provides a sheltered platform from which to launch once internal temperature reaches flight threshold. When a predator does attempt entry, the defensive choreography unfolds in tight quarters. A small mammal probing the hole with a claw encounters immediate resistance. The female braces her legs against tunnel walls, anchoring herself as she thrusts her abdomen outward. The confined space amplifies her advantage. There is no room for a predator to maneuver or avoid the sting. Should the intruder retreat, she advances just enough to maintain dominance of the threshold, then repositions deeper within once the threat subsides. The corridor remains silent again, its narrowness both shield and strategy. In this carved sanctuary, protection is embedded in geometry. The fortress does not announce itself with towers or visible battlements. It is concealed within the grain of wood, defined by absence rather than addition. Each tunnel represents an investment of time and energy balanced against the risk of predation and environmental stress. The Carpenter Bees solution is neither elaborate nor communal on the scale of social insects, yet it demonstrates a principle common across ecosystems. Survival often depends less on aggression than on intelligent design. By turning wood into a controlled microhabitat with a single defensible entrance, the Carpenter Bee transforms a vulnerable brood into a guarded lineage, secured by architecture that forces every predator to face the choke point where defender and fortress become one. Beneath the overhang of a roof beam, suspended from a slender stalk no thicker than a twig, hangs a structure that resembles weathered parchment sculpted into layered tiers. Its surface ripples in pale grays and muted browns, fibrous and matte, yet remarkably strong for something fashioned from chewed wood and saliva. This is not a passive shelter, but a fortress of paper engineered by wasps, its cells arranged in open combs that reveal rows of hexagonal chambers. Unlike the concealed tunnels of bees that prefer darkness, many social wasps construct exposed nests, relying not on invisibility, but on vigilance, speed, and aggression to secure their brood. The architecture is lightweight, suspended to reduce access from crawling predators, and designed for expansion as the colony grows through the warm months. The process of building begins with solitary queens in early spring. After emerging from overwintering sites where they survived in diapause, their metabolism slowed to endure cold scarcity, they seek suitable locations protected from wind and rain. With mandibles adapted for scraping fibers from weathered wood or plant stems, they gather material and mix it with saliva, creating a pulp that dries into paper upon exposure to air. Each strip is layered carefully, the fibers interlocking to form a composite that resists tearing and sheds water efficiently. The first cells are constructed downward from a central pedicel, a narrow attachment point that reduces the surface area accessible to ants and other crawling invaders. The queen lays eggs within these initial chambers and tends them alone until the first workers emerge. Once a workforce exists, nest construction accelerates dramatically, with new comb layers added and sometimes enveloped within protective outer walls that insulate against temperature fluctuations. Temperature regulation within a wasp nest depends heavily on location and behavior rather than complex ventilation systems. Workers fan their wings at the nest entrance to circulate air during hot spells, while others position themselves as living shades, clustering on the sunlit side to reduce heat gain. The paper envelope, when present, creates a buffered microclimate, reducing rapid thermal swings that could disrupt larval development. Because larvae are ectothermic and reliant on ambient warmth for growth, maintaining moderate temperatures ensures synchronized development and efficient resource use. Unlike honeybees, wasps do not store large quantities of honey for winter survival. Their colonies are seasonal, peaking in late summer before declining as temperatures drop. This annual cycle shapes their defensive temperament. Late in the season, as food becomes scarce and brood numbers reach maximum density, aggression intensifies. The nest entrance functions as a perpetual checkpoint, though less formalized than in bees. Workers patrol constantly, walking across the comb surface and hovering near the outer envelope. Their compound eyes, attuned to motion, detect approaching disturbances rapidly. Antennae sample chemical cues to distinguish colony members from intruders, and any unfamiliar scent triggers heightened alertness. Predatory threats vary by habitat. Birds may attempt to snatch larvae from exposed comb, while mammals such as raccoons or skunks may tear into nests to consume brood. Even other wasps may attempt to infiltrate and steal resources. In response, defenders exhibit threat displays before escalating to attack. They raise their bodies, wings vibrating in short bursts, and orient toward the source of disturbance. This posture is not mere theatrics. It communicates readiness to sting and may deter smaller predators that rely on assessing risk before committing. If the threat persists or makes contact with the nest, the counterattack unfolds with startling speed. Unlike species that retreat deeper into tunnels, social wasps surge outward. Workers launch from the comb in coordinated waves, guided by alarm pheromones released from venom glands. The chemical signal spreads rapidly through the air, marking both the nest site and the intruder as focal points. Within seconds, dozens or even hundreds of wasps converge on the disturbance. Their flight is direct and forceful, driven by powerful thoracic muscles capable of sustained pursuit. Stings are delivered repeatedly, as wasps possess smooth stingers that can be withdrawn without tearing from the body. Venom composition varies among species, but typically includes compounds that induce pain, inflammation, and local tissue disruption, creating an immediate deterrent. Speed itself is a defensive tool. The sudden eruption of wasps from a quiet nest creates a sensory shock for predators, unprepared for such rapid escalation. Many vertebrates learn quickly to associate the visual pattern of a suspended paper nest with the memory of painful encounters. The wasp's willingness to pursue beyond the immediate nest area further amplifies this deterrence. They may chase an intruder for several meters, maintaining attack formation until the perceived threat retreats fully. This pursuit behavior reduces the likelihood of repeated probing and reinforces territorial boundaries. In effect, the fortress extends beyond its physical walls into the surrounding airspace, defended by mobile sentinels. Within the comb, larvae play an indirect role in the colony's defense strategy through nutritional exchange. Adult wasps are primarily nectar feeders, requiring carbohydrates for flight energy, while larvae consume protein in the form of chewed insects delivered by workers. In return, larvae secrete droplets rich in amino acids that adults ingest, creating a feedback loop that ties brood health to adult vigor. This trophylactic exchange strengthens colony cohesion and ensures that defenders are fueled for rapid response. The ecological implications extend outward, as wasps regulate populations of caterpillars and other herbivorous insects, acting as natural pest control agents. Their predatory efficiency influences plant health and shapes community dynamics within their habitat. The structure of the nest itself contributes to defense through visibility. An exposed comb allows workers to detect vibrations instantly. The pedicel attachment acts as a flexible shock absorber. When disturbed, the nest sways, transmitting mechanical cues that alert interior workers before direct contact occurs. Some species even apply a chemical ant repellent to the pedicel, reducing the risk of ground-based invasion. These layered strategies reveal that aggression is not reckless, but integrated into architectural and chemical systems designed to maximize survival within a limited seasonal window. As summer matures and the colony reaches its peak population, reproductive individuals emerge. New queens and males prepare for dispersal flights that will ensure genetic continuity beyond the lifespan of the current nest. During this period, defensive intensity may reach its highest level. The colony has invested significant energy into producing reproductives, and any threat to the nest now jeopardizes future generations. The wasp's readiness to attack reflects this biological urgency. Yet as autumn advances and temperatures decline, workers gradually die off, and only newly mated queens seek sheltered crevices to overwinter. The once bustling fortress becomes silent, its paper walls weathering under rain and wind until they disintegrate. Standing beneath the eaves again, one can observe the duality of fragility and ferocity embodied in the wasp nest. The paper walls are thin enough to tear by hand, yet the defense they provoke is formidable. Architecture, behavior, and chemistry combine to create a system where intimidation and speed compensate for material lightness. The fortress is not meant to endure for years. It is designed for a season of intense productivity and equally intense defense. When disturbed, the response is immediate and overwhelming, a surge of wings and stingers that transforms a quiet afternoon into a whirring storm. Through this strategy, wasps secure their brood not by hiding within impregnable walls, but by projecting power outward, turning the air itself into an extension of their stronghold. At the edge of a humid forest clearing, where sunlight filters through broad leaves and lingers in suspended droplets of morning moisture, a nearly invisible architecture stretches between branches. It reveals itself only when light strikes at a certain angle, igniting strands into brief flashes of gold. Suspended within this lattice waits the golden Silk Orb-weaver, her long legs extended along radial lines, body poised at the hub of a web that is both residence and weapon. The fortress she inhabits does not enclose space in the way walls do. Instead, it defines a field of tension, a geometrical trap engineered from protein fibers that rival steel in tensile strength relative to weight. To step into this space unaware is to activate a defensive system calibrated by vibration, geometry, and speed. The web begins with anchor lines cast into open air, silk extruded from spinnerets at the spider's abdomen and carried by subtle currents until they snag on bark or leaf. These initial strands function like suspension cables, distributing load across multiple points to withstand wind and the impact of flying insects. From these anchors, the spider constructs a frame, then lays radial threads converging toward a central hub. These radii are not adhesive, they serve as highways, structural beams along which the spider can travel without entanglement. Between them, she spins a temporary spiral of non-sticky silk to measure spacing, later replacing it with a permanent spiral coated in adhesive droplets. These capture threads are elastic and viscid, designed to absorb the kinetic energy of prey in flight. Each droplet contains glycoproteins and hygroscopic compounds that maintain stickiness by absorbing moisture from the air, ensuring functionality even in fluctuating humidity. The geometry of the orb web is not random symmetry, but an optimized pattern balancing material investment with prey interception probability. Larger webs intercept more insects, but require greater metabolic expenditure to produce silk, which is synthesized from amino acids derived from previous meals. The golden hue of the silk, particularly pronounced in some species, may serve multiple functions. It can blend with sunlit foliage, rendering the web less visible to insects attuned to ultraviolet patterns, while simultaneously attracting certain prey that navigate by light gradients. The coloration may also strengthen silk fibers by incorporating pigments that modify structural properties. Within this architecture, defense and predation are inseparable. The web protects the spider from direct confrontation while simultaneously extending her sensory field. Unlike social fortresses guarded by patrolling sentinels, this system relies on tension and vibration as early warning signals. Each strand transmits mechanical information to the spider's highly sensitive slit sensilla located on her legs. These organs detect minute changes in strain, allowing her to distinguish between the chaotic flutter of a leaf-brushing silk and the rhythmic thrashing of a trapped insect. The web functions as an externalized nervous system, amplifying and directing signals across its surface. When an insect collides with the capture spiral, adhesive droplets stretch and elongate, dissipating energy while adhering to wings and legs. The prey's struggle only increases entanglement as elastic threads recoil and bind more tightly. At the hub, the spider interprets vibration frequency and amplitude to assess prey size and location without relying on vision alone. The counterattack unfolds in a rapid sprint across non-adhesive radial lines. The spider accelerates with precision, navigating the lattice without becoming ensnared. Her legs avoid sticky spirals instinctively, guided by spatial memory encoded during web construction. Upon reaching the prey, she deploys silk in swift arcs, wrapping the insect in swathing bands extruded from specialized spinnerets. This wrapping silk differs from structural lines. It is finer and produced rapidly, encasing the prey before it can inflict damage. Only once immobilization is complete does she deliver a venomous bite, injecting digestive enzymes that begin external digestion. The wall has transformed into a trap, and the trap into a delivery system for sustenance. The web's layered design includes additional features that serve defensive purposes beyond prey capture. Some orb weavers incorporate barrier threads above and below the main plane, forming a loose three-dimensional network that intercepts larger intruders, such as birds or small mammals, before they can crash into the primary web. These barrier lines absorb shock and redirect force, preserving the integrity of the capture spiral. In certain contexts, the spider may construct a retreat line leading to a concealed leaf or crevice nearby. When vibrations indicate an approaching predator too large to subdue, she can drop along a drag line, vanishing into vegetation while maintaining a connection to her web. This silk lifeline functions as both escape route and tether, allowing her to return once danger passes. Environmental factors continuously shape the fortress. Wind can tear sections of silk, requiring nightly reconstruction. Ultraviolet radiation degrades proteins, necessitating regular replacement of strands to maintain strength. The spider often consumes damaged silk, recycling amino acids to reduce energetic cost. Dew accumulation each morning increases web weight, but it also highlights geometry, revealing the structure to observers, while possibly deterring some insects that detect reflective surfaces. In regions with heavy rainfall, web placement under partial canopy cover reduces direct impact. The choice of site reflects an understanding encoded in instinct. Proximity to insect flight corridors, such as forest edges or clearings, increases capture rates, while excessive exposure to predators decreases survival. Predator interactions reveal additional layers of strategy. Birds sometimes learn to avoid golden webs after unpleasant encounters. Yet some species specialize in plucking spiders from their hubs. In response, orb weavers may construct stabilimenta, zigzag silk patterns whose function remains debated. These structures may strengthen the web, camouflage the spider, or warn larger animals of the web's presence to prevent accidental destruction. In some cases, stabilimenta reflect ultraviolet light strongly, potentially attracting prey that navigate by polarized light. Whether signal or reinforcement, these additions alter the visual signature of the fortress, demonstrating adaptive experimentation across species. Thermoregulation plays a subtle role in web behavior. The spider's metabolic rate increases with temperature, influencing silk production speed and prey processing. During cooler mornings, she may orient her body to maximize solar absorption, elevating internal temperature to optimize responsiveness. Silk elasticity itself varies with humidity and heat, affecting capture efficiency. By rebuilding the web frequently, often daily, the spider ensures that material properties remain tuned to prevailing conditions. The fortress is therefore dynamic, reconstructed in response to environmental flux, rather than maintained as a static barrier. As dusk settles, insect activity intensifies. Moths and flies navigate through the dimming air, their flight paths intersecting the nearly invisible plane of silk. Each impact sends tremors along radial highways, and each tremor prompts assessment. Not every collision warrants pursuit. Small debris or unprofitable prey may be ignored to conserve energy. This selectivity reflects a cost-benefit calculation embedded in instinct. Silk is expensive to produce, and venom reserves must be allocated wisely. The orb weaver balances risk and reward with efficiency honed through countless generations. In the quiet that follows a successful capture, the web hangs once more in deceptive stillness, its geometry barely perceptible, except where starlight catches golden strands. The fortress remains open to the world, transparent and vulnerable in appearance, yet formidable in function. Its defense does not rely on intimidation or massed numbers, but on physics and speed, on tensioned lines that transform empty air into controlled territory. The spider's sprint across silk exemplifies a counterattack executed within her own architecture, where every thread serves both as wall and weapon. In this suspended domain, invisibility becomes strength, and the boundary between home and trap dissolves into a single shimmering design. In late summer, when meadow grasses rise tall and seed heads shimmer under a dry amber sun, a vertical corridor of open air stretches between stems. To passing insects, this narrow space appears like any other gap in the vegetation, a convenient flight path threading through a dense green labyrinth. Yet suspended within this corridor, nearly invisible except for a startling flash of white zigzag silk, waits the wasp spider. Her abdomen bears bold bands of yellow, black, and white, a warning palette that echoes the stinging insects she resembles. But her true power lies not in mimicry alone. It lies in geometry and placement. The web is not hidden in shadow nor tucked beneath a roof beam. It is built deliberately in open air, where the flow of insect traffic is greatest. The fortress here is not a shelter, but a hunting arena, a controlled battlefield engineered from silk and anticipation. The wasp spider constructs a classic orb web, yet its scale and orientation are tuned to meadow ecology. The web is positioned vertically between rigid stems, often aligned perpendicular to prevailing wind currents. This orientation increases the probability that flying insects navigating along wind corridors will intersect the capture spiral. The spider begins by releasing a dragline that catches on a distant stem, establishing the first anchor. From there, she reinforces the frame with multiple guy lines, tensioned carefully to withstand both wind sway and the impact of large prey. Radial threads extend inward like spokes of a wheel, converging at the hub where she will rest. Between them, she spins the adhesive spiral, each loop spaced with measured precision. At the center, she adds a stabilimentum, a bold zigzag band of dense silk that reflects ultraviolet light strongly. While its exact function remains debated, evidence suggests it may attract certain pollinating insects that perceive ultraviolet patterns as floral cues, effectively luring prey into the trap. The meadow is alive with motion. Grasshoppers leap in erratic arcs, bees travel direct routes between blossoms, and flies patrol the air in looping circuits. The wasp spider remains motionless at the hub, legs extended along radial lines. Her posture is not passive but calibrated. Sensory hairs on her legs detect the faintest tremor, converting mechanical vibration into neural signals with extraordinary sensitivity. The web functions as an extension of her body, amplifying disturbances across its surface. Unlike hidden tunnel dwellers or enclosed nests, this system exposes her fully to the environment. She relies on speed and decisiveness rather than concealment. When a large orthopteran, perhaps a grasshopper, collides with the web, the impact reverberates outward in waves. Adhesive droplets elongate and stretch, dissipating kinetic energy. The prey's instinctive thrashing only increases entanglement, elastic threads recoiling to tighten their hold. Within a fraction of a second, the spider has assessed the amplitude and frequency of vibration, distinguishing between wind-blown debris and substantial prey. She launches from the hub along a non-adhesive radial line, sprinting with precision that avoids sticky spirals she herself placed. The rush is direct and unhesitating. Upon reaching the struggling insect, she bites swiftly, injecting venom that begins to immobilize neuromuscular function. Simultaneously, she releases bands of wrapping silk, rotating the prey with rapid leg movements to encase it in a shroud of fine fibers. The counterattack is complete before the insect can free even one limb. This rapid response is essential in open air. Unlike species that retreat to a leaf retreat or rely on retreat lines for safety, the wasp spider occupies her web conspicuously. Any delay in subduing prey risks escape or damage to the web's structural integrity. The speed of her approach reduces these risks, turning potential loss into secured energy. Venom composition plays a role beyond simple paralysis. It contains enzymes that initiate digestion externally, breaking down tissues into absorbable fluids. The spider may leave wrapped prey suspended in the web as a reserve, returning later to feed, a strategy that buffers against fluctuations in insect availability. Web placement itself functions as defense. By situating the web within a corridor bordered by sturdy stems, she reduces the likelihood of large animals blundering through and destroying the structure. The stabilimentum may also serve as a visual warning to birds, preventing accidental collisions that could tear silk beyond repair. In this sense, the bright zigzag is both lure and shield, signaling presence to some organisms while attracting others. The dual function underscores the complexity of evolutionary trade-offs in open habitats. Environmental forces continuously test the arena. Wind gusts cause the web to oscillate, yet anchor lines distribute stress across multiple attachment points, preventing catastrophic failure. Morning dew accumulates on silk, increasing weight but also revealing the web's outline. The spider often repairs damage at dusk, consuming broken strands to recycle amino acids before respinning sections overnight. Silk production is metabolically costly. Proteins must be synthesized from dietary intake, linking prey capture success directly to architectural maintenance. The meadow's seasonal rhythms influence her strategy. In late summer, when insect biomass peaks, she may construct larger webs to capitalize on abundance. As temperatures decline, metabolic rates slow, and web size may decrease to conserve energy. Predator interactions in this open arena differ from those faced by concealed nest builders. Birds scanning vegetation may spot the spider's bright abdomen. Her coloration, resembling that of stinging wasps, likely functions as Batesian mimicry, deterring predators that associate such patterns with pain. Yet mimicry alone is imperfect protection. If threatened, she may drop from the web along a dragline, disappearing into grass shadows while maintaining a tether to her structure. This escape behavior blends retreat with retention. She abandons the arena momentarily, but preserves its framework for rapid return. The wasp spider's life cycle aligns with meadow phenology. Eggs are laid in autumn within a silk egg sac, concealed among vegetation, the mother dying shortly thereafter. Spiderlings overwinter within the sac, emerging in spring when insect populations begin to rise. Some disperse by ballooning, releasing silk threads that catch thermal currents and carry them to new territories. This dispersal strategy reduces competition and allows colonization of fresh hunting corridors. Migration here is not a coordinated journey like that of birds, but a wind-borne gamble, leveraging atmospheric physics to expand range. Within the hunting arena, defense and predation are inseparable processes. The web intercepts not only prey but also potential threats, transmitting information instantly. The spider's rapid rush, bite, and wrap sequence transforms intrusion into resource. There is no warning display, no prolonged standoff. The battlefield is defined by silk geometry and the spider's capacity for immediate action. Each successful capture reinforces the fortress, providing nutrients necessary for silk regeneration and reproductive investment. As evening light softens and the meadow cools, insects continue their flight paths, unaware of the invisible plane stretched across their route. The wasp spider remains poised, abdomen bright against fading green, her web shimmering faintly in angled light. The fortress is transparent yet decisive, open yet controlled. In this suspended arena, survival depends on anticipation and speed, on the ability to convert open air into territory governed by silk and reflex. Anything that strikes the web enters a domain where escape is measured in fractions of a second, and where the boundary between attacker and defender dissolves into a single swift motion across threads drawn tight against the wind. Beneath the decaying logs of a tropical forest in Madagascar, where humidity clings to the air and leaf litter forms a dense, damp carpet, the architecture of survival is already built. It exists not as raised towers or woven silk, but as fractures in bark, hollow spaces beneath rotting wood, and the layered cavities of decomposing trunks. Within these narrow voids moves the Madagascar hissing cockroach, a creature that does not construct fortresses of its own design, but instead claims the ruins of others. In this ecosystem, decay itself becomes a defensive structure, and survival depends on exploiting spaces too tight, too dark, and too irregular for predators to navigate efficiently. The cockroach's body, glossy and armored, is shaped not for elegance but for pressure, compression, and endurance inside these natural bunkers. The forest floor here is in constant transformation. Fallen trees soften under fungal invasion, their cellulose broken down by networks of mycelium that convert rigid wood into sponge-like corridors. Termites excavate galleries, beetle larvae chew tunnels, and microbes hollow the interior from within. What remains is a labyrinth of cracks and chambers that vary in width from open cavities to crevices barely larger than a coin. The Madagascar cockroach selects these micro-habitats deliberately. Its flattened body profile allows it to wedge into narrow gaps, legs braced against opposing walls. The exoskeleton is thick and smooth, composed of hardened chitin plates that resist compression and provide a shield against biting mandibles. In such confined spaces, a predator cannot achieve a full grip, and the cockroach's defensive strategy begins with this simple geometric reality. If you cannot be grasped cleanly, you cannot be subdued easily. Unlike ants or bees, this species does not rely on collective construction or coordinated defense. Its fortress is opportunistic, chosen rather than built. During daylight hours, individuals remain hidden within these cavities, avoiding desiccation and visual detection. The forest's high humidity is crucial. Cockroaches lose water rapidly through respiration, and remaining within moist crevices reduces evaporative stress. Their spiracles, the respiratory openings along the body, can close temporarily to limit water loss, an adaptation that allows survival during brief periods of lower humidity. Yet they do not wander far from shelter unless conditions favor activity. At night, when temperatures moderate and predators such as birds are less active, they emerge to forage on decaying plant matter and fallen fruit, contributing to nutrient cycling within the ecosystem. Predation pressure is constant. Small mammals, reptiles, and birds patrol the forest floor, probing logs and leaf litter for concealed prey. When a predator overturns a rotting branch, the cockroach reacts with remarkable speed. It does not sprint aimlessly across open ground unless no alternative exists. Instead, it dives toward the nearest crevice, compressing its body and wedging itself firmly inside. Specialized spines along its legs provide traction against rough surfaces, enabling it to push backward with force. Once inside, it lowers its body profile further, pressing the dorsal plates against the cavity ceiling. The armor serves as both shield and brace. Even if a predator inserts a claw or snout into the opening, the cockroach can anchor itself, distributing pressure across its exoskeleton and resisting extraction. The defensive repertoire extends beyond passive resistance. When threatened in close quarters, the Madagascar cockroach produces a sudden hiss, a sharp expulsion of air forced through modified spiracles. This sound is not vocal in origin but pneumatic, generated by muscular contractions that propel air outward rapidly. The hiss can serve multiple functions, startling predators, signaling distress, or asserting dominance during encounters with conspecifics. In the confined acoustics of a hollow log, the sound is amplified, transforming a small insect into a surprisingly loud presence. The element of surprise can cause a predator to hesitate just long enough for the cockroach to reposition deeper into safety. In some cases, individuals will push aggressively against an intruding object, using their sturdy pronotum, the shield-like plate behind the head, to shove and resist. This refusal to yield within confined spaces exemplifies a counterattack rooted in intimidation and physical resistance rather than venom or speed. The armor itself reflects evolutionary investment. The cuticle is reinforced with layers that provide rigidity while maintaining flexibility at jointed segments. This design allows the cockroach to absorb compressive forces without fracturing. Molting cycles accommodate growth, but adults retain a hardened exterior capable of withstanding significant pressure. Predators that rely on crushing bites may find limited purchase on the smooth surface, and the cockroach's ability to tuck its head beneath the pronotum reduces vulnerable exposure. The low profile, combined with behavioral choices, creates a defense system that thrives in environments defined by decay and fragmentation. Symbiotic relationships further enhance survival within these ruined fortresses. The cockroach's digestive tract hosts microorganisms capable of breaking down cellulose, enabling it to extract nutrients from decomposing plant material that many animals cannot utilize directly. This mutualistic association allows it to occupy ecological niches centered on detritus, reducing competition with species dependent on fresher food sources. By consuming decaying matter, it contributes to nutrient recycling, accelerating the return of organic compounds to the soil. In this sense, the cockroach is both resident and custodian of the forest's ruins, participating in the very processes that generate its shelter. Reproductive behavior unfolds within these hidden chambers. Males establish small territories in favored cavities, using hissing displays and physical pushing to compete for access to females. The contests rarely result in severe injury, but involve persistent shoving matches where each male attempts to dislodge the other from the prime crevice. The winner secures a strategic shelter that offers both protection and proximity to mates. Females carry ootheca internally until the young are ready to emerge, giving birth to live nymphs that resemble miniature adults. This reproductive strategy reduces exposure of eggs to environmental hazards and predators, aligning with the species' preference for concealed development. Thermoregulation in this tropical environment relies largely on behavioral adjustment. By shifting position within logs, the cockroach can move closer to the cooler, damp core during hotter periods or nearer the surface when temperatures drop slightly at night. The insulating properties of decaying wood buffer rapid thermal fluctuations, creating microclimates that remain relatively stable compared to exposed forest floor. The reliance on pre-existing structures means that habitat loss or removal of fallen timber can significantly impact populations, underscoring the ecological importance of dead wood in forest systems. As dawn approaches and humidity condenses into fine droplets on leaf litter, the cockroach retreats fully into its chosen cavity. The forest quiets, and predators resume diurnal patrols above ground. Within the narrow space, the insect remains motionless, armored plates pressed against irregular surfaces, antennae extended slightly to sample chemical traces drifting through the opening. It does not seek confrontation, yet it is prepared for it. Should a probing claw or curious snout intrude, the response will be immediate. A forceful hiss, a shove, a steadfast refusal to be pulled free. The fortress may not bear its maker's signature, but it is defended with persistence and anatomical advantage. In these dim recesses of tropical decay, survival belongs to those who understand space as strategy. The Madagascar hissing cockroach exemplifies a form of defense rooted not in architectural grandeur or collective swarms, but in the disciplined use of confinement. Armor, low profile, and acoustic intimidation combine within borrowed ruins to create a system where predators struggle to gain leverage. Amid the slow crumble of wood into soil, the cockroach thrives, turning the forest's constant breakdown into a stronghold shaped by pressure, sound, and unyielding presence. Out on the open savanna, where heat shimmers above sun-baked grass and the horizon stretches in wavering bands of gold, survival often begins with what others leave behind. A fresh deposit of herbivore dung steams faintly in the morning air, its scent dispersing rapidly across the landscape. Within minutes, the first dung beetles arrive, navigating not by sight alone, but by olfactory precision, capable of detecting volatile compounds carried on the wind from remarkable distances. To larger animals, the dung is refuse, an afterthought in the daily rhythm of grazing. To the beetle, it is foundation, fortress, nursery, and future. The surface of the dung pile becomes a scene of urgent activity. Beetles land, assess texture and moisture with antennae that end in lamellate clubs, designed to trap scent particles, and begin carving sections free with spade-like forelegs. Some species remain at the source, tunneling directly beneath it, while others shape fragments into nearly perfect spheres and roll them away across the uneven ground. The rollers move with determination, walking backward as they push their cargo with hind legs, occasionally climbing atop the ball to orient themselves using celestial cues. Even under intense daylight, some species use the sun's position as a compass, adjusting trajectory in straight lines to escape competition. At night, others orient by the glow of the Milky Way, a rare example of invertebrate navigation guided by the broad sweep of stars. The rolling itself is not random dispersal. It is the first phase of fortress construction. By removing a portion of dung from the crowded surface, the beetle reduces the likelihood of theft and parasitism. Competition around fresh dung is fierce. Dozens of individuals may grapple over fragments, attempting to pry away pieces with hooked legs and powerful mandibles. Larger beetles can overturn smaller rivals, while equally matched opponents engage in shoving contests that resemble miniature wrestling matches. These conflicts are not aimless aggression, but resource warfare, driven by the knowledge that dung represents both immediate sustenance and the substrate for reproduction. Once a beetle has secured its ball and rolled it a sufficient distance, it begins excavation. Using forelegs adapted for digging, it buries the sphere beneath the soil, carving a vertical or slanted tunnel that leads to a chamber just large enough to house the dung mass. Underground, temperature and humidity stabilize relative to the exposed surface. Soil acts as insulation, buffering extreme heat during midday and retaining moisture that prevents desiccation of the resource. In this concealed chamber, the beetle shapes the dung further, sometimes dividing it into brood balls, each carefully smoothed and provisioned with a single egg laid within a small cavity. The fortress is now complete, buried walls of soil surrounding a nutrient core that will sustain developing larvae. Secrecy is the primary defense. Above ground, dung attracts predators and parasites ranging from birds to ants and parasitic flies that lay eggs in exposed masses. By moving the resource underground, the beetle effectively removes it from open view and reduces scent dispersion. Soil absorbs and diffuses odor molecules, masking the exact location of the chamber. A predator scanning the savanna surface sees nothing more than undisturbed earth. Even if it senses faint traces, the depth of burial complicates excavation, particularly when chambers are constructed beneath compacted or root-bound soil. Within the buried sphere, a larva will hatch and feed gradually, consuming the dung from the inside outward. The spherical architecture serves multiple functions. Its shape minimizes surface area relative to volume, reducing moisture loss and microbial contamination. It also provides structural stability. Pressure from surrounding soil distributes evenly across the curved surface, preventing collapse. As the larva grows, it remains insulated from many surface threats, completing its development before emerging as an adult beetle capable of flight. Not all dung beetles roll balls away. Tunnelers excavate directly beneath the dung pile, dragging portions downward into branching galleries. These subterranean networks can extend several centimeters below ground, with multiple chambers branching from a central shaft. The tunnels themselves act as defensive corridors. If a predator disturbs the surface pile, the beetles retreat downward, sealing entrances loosely with soil. In this architecture, the fortress is layered vertically rather than horizontally dispersed across the landscape. Resource theft remains a constant risk even after burial. Rival beetles may track rolling individuals and attempt to intercept them before excavation begins. Some species have evolved horns used in combat, structures that provide leverage during pushing contests. Males with larger horns often secure greater reproductive success by defending tunnels and access to females. Sexual selection therefore shapes not only mating systems, but the intensity of resource warfare around dung fortresses. The outcome of these battles determines which genes persist in future generations, linking competition directly to evolutionary trajectory. The ecological implications of dung burial extend far beyond individual survival. By relocating and interring dung, beetles accelerate nutrient incorporation into soil, enhancing fertility and reducing parasite loads in grazing systems. Their activity improves soil aeration and water infiltration, creating microhabitats favorable to plant growth. In agricultural landscapes, dung beetles reduce the persistence of livestock parasites by removing breeding grounds from the surface. Thus, the fortress built for personal survival simultaneously contributes to ecosystem health, illustrating how individual strategies can scale to landscape-level processes. Thermoregulation plays a subtle but significant role in burial behavior. In open savanna, surface temperatures can rise dramatically under direct sunlight, desiccating dung rapidly. By burying it, beetles preserve moisture essential for larval development. Soil depth selection often reflects temperature gradients. Deeper chambers remain cooler and more stable, while shallow burials may suffice in milder climates. Some species adjust burial depth seasonally, responding to rainfall patterns and soil composition. The fortress is therefore dynamic, shaped by microclimatic awareness encoded in instinctual behavior. Predator interactions occasionally disrupt even buried strongholds. Mammals such as mongooses may dig in areas with high beetle activity, seeking larvae as protein-rich prey. When tunnels are breached, adult beetles may attempt to defend their brood, using mandibles and horns to push against intruders. Yet their primary strategy remains concealment. Unlike social insects that swarm in coordinated defense, dung beetles rely on reducing visibility and dispersing risk. By spreading brood balls across different locations, they avoid concentrating all investment in a single vulnerable site. As evening approaches and shadows lengthen across the grassland, new dung deposits appear, and the cycle begins again. Beetles emerge from burrows, drawn by scent plumes drifting in cooling air. The battlefield reforms around each fresh resource, and once more individuals carve, roll, and bury with urgency. The savanna may seem vast and open, yet beneath its surface lies a network of hidden chambers, each containing a sphere of life sealed within earthen walls. In this world, waste becomes architecture, and concealment becomes defense. The dung beetle's fortress is not visible from a distance, nor does it rise above the horizon. It exists beneath the soil, where secrecy shields both sustenance and offspring. Through strength, navigation, and persistent excavation, these beetles transform ephemeral deposits into enduring strongholds. In doing so, they demonstrate that survival often depends not on overt aggression or imposing structures, but on the disciplined art of removing value from the open and burying it where only the determined can find it. In the layered stillness of a tropical forest understory, where shafts of filtered light drift between overlapping leaves, and the air hangs warm with suspended moisture, survival often depends not on strength or speed, but on disappearance. Among the interlaced branches, a slender twig juts outward at an unremarkable angle, textured with faint ridges and softened by moss. It seems fixed, part of the plant itself, until a subtle shift reveals the faint articulation of jointed legs. The stick insect does not build a fortress of soil or silk, nor carve tunnels into wood. Its fortress is the forest itself, and its walls are made of deception. When form, color, and motion align with the background, the boundary between organism and environment dissolves, and the safest structure becomes invisibility. The body of the stick insect is elongated and segmented in proportions that mimic the geometry of stems. Pigmentation matches the bark or foliage of its host plants, often incorporating irregular patches that resemble lichen or shadowed nodes. Some species bear small protrusions along their thorax and abdomen that imitate leaf scars or budding growth points. These features are not decorative, but functional, shaped by generations of selective pressure from visually hunting predators such as birds and reptiles. In habitats where predation intensity is high, individuals whose morphology most closely resembled surrounding vegetation were more likely to survive and reproduce. Over evolutionary time, this process refined the illusion to a remarkable degree. Camouflage alone is insufficient if movement betrays presence. The stick insect's primary defensive behavior is stillness, an extreme form of motion suppression that can last for hours. Muscles remain engaged to maintain posture, legs locked at angles that mirror nearby twigs. When wind stirs the foliage, the insect may sway gently in synchrony, matching the oscillation frequency of surrounding leaves. This behavior, known as sway mimicry, reduces the risk that slight movements will stand out against a dynamic background. The forest is rarely static. Leaves tremble, stems flex, and shadows shift with passing clouds. By aligning its motion with environmental rhythms, the stick insect merges into the collective movement of vegetation, transforming the entire habitat into an extended protective structure. Predators rely heavily on pattern recognition. A bird scanning branches for caterpillars or beetles detects anomalies in shape, color, or motion. The stick insect's strategy exploits the cognitive limitations of such search behavior. When an organism so closely resembles inanimate elements of the environment, the predator's visual system may filter it out as irrelevant background. This phenomenon, sometimes described as crypsis, is not merely about blending colors, but about matching spatial frequencies and contours. Even the insect's eyes are small and subdued, minimizing reflective surfaces that could catch light and reveal identity. In effect, the stick insect occupies a perceptual blind spot within the forest. The fortress of deception extends to reproductive strategy. Many stick insects lay eggs that resemble plant seeds, complete with textured surfaces and appendages that mimic nutrient-rich structures known as eliosomes. Ants, attracted to these appendages, carry the eggs to their nests, consume the nutrient portion, and discard the intact egg in protected underground chambers. This incidental transport, a form of myrmecochory, shields eggs from surface predators and environmental extremes. The insect leverages ant behavior to extend its fortress beyond the canopy and into the soil, without constructing any protective structure of its own. It is an elegant example of symbiotic exploitation, where one species' foraging instinct becomes another's defense. When direct threat approaches too closely for camouflage to suffice, the stick insect employs secondary defenses. Some species can shed a leg in a process called autotomy, sacrificing a limb to escape grasp. The lost appendage may twitch, distracting the predator while the insect drops silently to the forest floor. Remarkably, juveniles can regenerate lost legs over successive molts, restoring functionality before adulthood. This capacity reflects an evolutionary trade-off between immediate survival and temporary impairment. In other species, sudden displays of hidden coloration beneath wings may startle predators momentarily, creating a flash of unexpected color that disrupts attack. Yet such behaviors are rare and reserved for imminent danger. The primary strategy remains psychological rather than physical. Delay detection, confuse search patterns, and conserve energy. Energy efficiency is central to this lifestyle. Unlike active hunters or builders that invest heavily in construction or combat, stick insects minimize metabolic expenditure by relying on passive defense. Their diet of leaves provides limited nutritional density, and digestion of plant material requires symbiotic gut microorganisms capable of breaking down cellulose. By remaining motionless for extended periods, they reduce exposure to predators and conserve scarce energy reserves. Thermoregulation is largely behavioral. Individuals may adjust position within the canopy to balance sunlight exposure and shade, avoiding overheating while maintaining sufficient warmth for metabolic processes. Because they are ectothermic, ambient temperature influences activity levels. During cooler periods, reduced movement further enhances camouflage, as stillness becomes both thermal adaptation and defense. The counterattack of the stick insect is subtle but effective. When a predator commits time and attention to scanning a branch only to find nothing, that time is lost. In ecosystems where hunting success depends on efficiency, wasted search effort reduces overall predation rate. The insect may then slip slowly along a branch when the predator's focus shifts elsewhere, moving with deliberate caution that avoids abrupt motion. This near-costless escape capitalizes on the predator's cognitive biases. Unlike species that rely on speed bursts or venom injections, the stick insect's defense operates at the level of perception. It alters the battlefield by manipulating what is seen and what is ignored. Occasionally, environmental change challenges this fortress. Seasonal shifts in foliage color can render once effective camouflage conspicuous. Some species respond by altering pigmentation gradually through molting cycles, matching new leaf hues as the canopy transitions. Others occupy microhabitats where background remains consistent year-round. Such adjustments illustrate that deception is not static, but responsive to ecological context. The success of camouflage depends on constant alignment between organism and environment. As dusk deepens and the forest transitions into nocturnal rhythm, the stick insect may begin to feed more actively. Darkness reduces reliance on visual camouflage, yet even then, movement remains measured. Antennae extend forward, sampling air currents and plant surfaces for suitable leaves. The fortress persists because the insect never truly leaves it. Every branch and leaf remains potential cover. When dawn returns and diurnal predators resume patrol, the insect reassumes its rigid posture, once again becoming indistinguishable from surrounding twigs. In this realm of layered foliage and filtered light, the strongest walls are not those that block entry, but those that prevent notice. The stick insect exemplifies a defensive philosophy rooted in absence rather than confrontation. By transforming the environment into its own protective architecture, it avoids the need for heavy armor or aggressive retaliation. Predators search, hesitate, and move on, their efforts dissolved into the background of leaves and branches. Within this living fortress of deception, survival unfolds quietly, governed by stillness, subtle sway, and the profound advantage of being unseen. In the dry heat of a desert plain, where the ground fractures into hardened plates and sparse shrubs cast thin, trembling shadows, survival is etched into the soil itself. Beneath a flat stone warmed all day by relentless sun lies a narrow opening no wider than a finger. It descends into darkness, a shallow burrow carved into compacted earth, its walls smoothed by repeated passage. Within this bunker waits the black scorpion, a predator armored in chitin and patience. Unlike insects that construct elaborate nests or webs, the scorpion claims pre-existing shelters or excavates modest tunnels, transforming cracks and crevices into defensive strongholds. In an environment where exposure can mean dehydration or predation, concealment beneath stone becomes both refuge and hunting platform. Daytime temperatures on the desert surface can rise beyond levels tolerable for many arthropods. The scorpion's exoskeleton reduces water loss, yet it is not immune to desiccation. By retreating into burrows or beneath rocks, it exploits the insulating properties of soil, where temperature fluctuations are dampened and humidity remains slightly higher than in open air. The burrow is rarely deep, but even a few centimeters below the surface can mean the difference between lethal heat and survivable warmth. Some species excavate their own tunnels using pedipalps and legs, loosening soil grain by grain, while others occupy abandoned insect burrows or natural fissures in clay. The architecture is simple yet effective, a narrow entrance leading to a widened chamber where the scorpion can rest, protected from both thermal extremes and visual predators. As dusk approaches and heat dissipates from the sand, the scorpion shifts from refuge to sentinel. It positions itself at the burrow entrance, claws extended slightly forward, tail arched but not yet poised to strike. Its sensory world is defined not by sharp vision, but by vibration. Specialized hairs called trichobothria along the pedipalps detect subtle air movements, while slit sensilla on the legs register minute ground vibrations. In darkness, where sight offers limited advantage, these mechanosensory structures become the primary means of perceiving approaching prey or threat. The burrow entrance functions as a choke point and observation post. Anything crossing nearby ground transmits tremors through the substrate, revealing size, direction, and speed. The desert night is alive with small movement. Beetles scuttle in search of detritus, crickets hop between sparse vegetation, and the occasional rodent passes cautiously across open ground. When vibrations match the signature of suitable prey, the scorpion does not charge blindly. It waits until the insect ventures within striking range, conserving energy in a landscape where meals are unpredictable. Then, in a motion so swift it blurs even under close observation, the pedipalps snap shut. The claws clamp first, securing the prey mechanically before venom is deployed. Only once control is established does the stinger arc forward, delivering a measured injection. Venom composition varies by species, often containing neurotoxins that disrupt ion channels in nerve membranes, leading to paralysis. The sting is not wasted on distant targets. It is applied with precision once escape is no longer possible. Prey subdued, the scorpion drags its catch backward into the burrow. The act is deliberate, ensuring that feeding occurs within the fortress rather than in open terrain where larger predators might intervene. Inside the chamber, digestive enzymes are applied externally, liquefying tissues that can be ingested through the scorpion's narrow mouthparts. Feeding may last hours, and remnants are often left within the burrow, later desiccated by the dry air. The bunker thus serves multiple purposes: shelter, ambush site, and dining chamber, shielded from interruption. Defense extends beyond hunting strategy. If threatened by a larger predator, such as a lizard probing beneath rocks, the scorpion relies first on stillness. Its dark coloration blends with shadowed soil, reducing visual detection. If contact becomes imminent, it may raise its metasoma, the segmented tail, in a defensive arch. The pedipalps spread wide, presenting an imposing silhouette relative to its size. In confined spaces, this posture makes extraction difficult. A predator inserting a snout into the burrow faces immediate resistance as claws clamp onto sensitive tissue and the sting follows in rapid succession. Some desert predators have evolved partial resistance to scorpion venom, yet the risk of pain or injury often deters repeated attempts. The scorpion's physiology reveals adaptations finely tuned to arid survival. Its metabolic rate is low, allowing it to endure long periods without food. Studies have shown that some species can survive months between meals, relying on stored energy reserves. Water needs are met largely through metabolic processes and moisture contained in prey, reducing dependence on scarce surface water. Spiracles open intermittently to limit evaporative loss, and the waxy cuticle further minimizes dehydration. In cooler months, activity may decrease, with individuals remaining within burrows for extended periods until conditions favor movement. Reproduction also unfolds within these protective structures. Courtship involves a complex dance in which male and female grasp each other's pedipalps and move across the ground in search of a suitable substrate for sperm transfer. After mating, the female may return to her burrow, where she will later give birth to live young rather than laying eggs. The offspring climb onto her back, clinging there until their first molt. During this vulnerable stage, the burrow becomes a nursery bunker, shielding both mother and young from environmental extremes and predators. The maternal investment is notable among arthropods, underscoring a strategy that combines shelter with extended care. Ecologically, scorpions occupy a critical role as nocturnal regulators of insect populations. By preying on crickets, beetles, and other arthropods, they influence community composition in desert ecosystems. In turn, they serve as prey for specialized predators, such as certain owls and mammals capable of handling venomous arthropods. This dynamic interplay shapes evolutionary arms races, where venom potency and predator resistance co-evolve over time. As midnight deepens and the desert cools further, the scorpion remains at its threshold, neither fully exposed nor entirely concealed. The burrow entrance frames its silhouette against starlit sand, a gatekeeper poised between refuge and opportunity. The fortress here is understated, carved into earth rather than raised above it, yet its strategic value is immense. By combining shelter with ambush, the scorpion transforms a simple hole in the ground into a controlled domain where prey is intercepted and threats are confronted on favorable terms. When dawn begins to pale the horizon and temperatures hint at the coming heat, the scorpion withdraws fully into its chamber. The entrance appears empty, indistinguishable from countless other cracks in the desert crust. Yet beneath the surface, within that modest bunker, a predator rests secure, armored and patient. In this final example of fortress survival, defense and counterattack merge seamlessly. The burrow shields from sun and predator alike, while the night ambush ensures sustenance. In the austere landscape of sand and stone, the black scorpion endures not through grand construction or overwhelming force, but through mastery of concealment, sensory acuity, and decisive measured violence at the gate of its earthen stronghold.